The last item we're going to consider is energy density in electrostatic fields. So the approach we're going to take here is we're going to say that the energy in the system is equal to the work required to move the charges into the system. So we're essentially stating conservation of energy. So if we have to exert X amount of energy to put something in the system is going to gain X amount of potential energy and then therefore have that much energy density, or we're going to work our way towards the energy density. So let's start by considering point charges. So point charges are usually a good starting point. They're relatively simple to deal with. So let's start by just looking at a system of a few point charges. So let's start by bringing 3 point charges from infinity to 3 points. So bringing Q1, Q2, and Q3, so 3 point charges of whatever value we want them to be, to points P1, P2, and P3 respectively. All right, so our total energy in the system then is going to be W sub E, and we're going to say this is equal to the energy it takes to bring our first point charge into the system, plus the energy it takes to bring the second point charge into the system, plus the energy it takes to bring the third point charge into the system. And so as it turns out, for this first point charge, our Q1, if we assume there's nothing in the system initially, there's essentially nothing there to sort of repel it. So the easiest thing to think about is, let's say Q1, Q2, and Q3 are all positive valued. So if we have a positive point charge already in the system, that's going to be repelling our new point charge, and we're going to have to put in work. However, if we have nothing in our system initially, then we're going to require 0 work to bring that first point charge in. So using our definition of work from before, we know that it's equal to Q times V. So then to bring in the second point charge, that's going to require work Q2 times V21. And remember, that's the voltage at 1 reference to 2. And so what we're saying here is now this energy that we would require to bring this into the system is becoming part of the system's potential energy. So similarly for our third point charge, we're going to have Q3 times the potential, but now we have 2 point charges already in the system. So we have V31 plus V32. So we have to consider effects from both Q1 and Q2. So what we can show, and we're not going to go into the details, but if you want to see that, you can look on page 154, is that we can rewrite this energy, W sub E, as 1/2 times Q1 times V1 plus Q2 times V2 plus Q3 times V3. And so now, instead of having these potential differences which we had in our previous equation, we have total potentials. So our V1, our V2, and our V3 are the total potentials at points 1, 2, and 3 respectively. So these are our total potentials. So with this more generalized equation, of course, that becomes pretty easy to scale up for multiple point charges. So we can, let's say, generalize for n point charges. All right, so if we have n point charges, we can then say the energy, capital W of E in the system is equal to, so we have that 1/2 factor out front, and then we have the summation from k equals 1 to n of our charge of our kth point charge times the potential at position k where that point charge is located. And so this energy is going to be in units of joules, and we're not going to have time to look through and practice using this equation, but if you do want to get some practice with that, you can look at example 4.14 on page 156 in the textbook. Okay, so this is how we can deal with our point charges, but let's say we want to deal with a continuous charge distribution. So continuous charge distribution, so these are our line charges, our surface charges, our volume charges. So what are we going to do if we have a continuous charge distribution? And we've actually already sort of seen this problem in a different context. Basically, to generalize this equation that's made for point charges, we're going to change our charge to a charge density. So we're going to have a charge density instead of just the charge value itself. So Q sub k is going to become a rho. And instead of summing, of course, we're just going to integrate. So simple as that. So I want to spend a little time talking more about volume charges in particular. The reason I want to do that is because oftentimes we want to know the electrostatic energy or the electrostatic energy density in a particular volume. So let's look at a volume charge. So if we have a volume charge then, sort of adjusting that general equation for multiple point charges, we have 1/2, and now instead of summing, we said we're going to integrate. So we're integrating over the volume, and instead of our Q sub k for our kth point charge, we're just going to have a charge density, rho sub v for the volume. We multiply by the potential in the region, and we have some differential volume for our integral. So we're again going to sort of skip over some of the details, but basically if we use Maxwell's first equation, which remember relates our rho v to our electric flux density d, as well as some other theorems and properties for our del operator and various things like that, what we can do is we can rearrange this and we get our WE, our energy in the system, is equal to 1/2 times the integral over the volume of d dot E times our differential volume dV. So again, if you want to see more details about that, you can look on page 155 in the text. So remember that our electric flux density D is simply equal to epsilon naught E. So what this becomes then, of course, E is going to be in the same direction of E. So if we go back to our basic definition of dot product, magnitude A, magnitude B, cosine of the angle between them. So the angle between them is 0, so that's just going to be 1. So this reduces to 1/2 integral over the volume of epsilon naught times the magnitude of our electric field squared dV. And so this is a simple equation we can use to find the energy in a volume in a certain region with a known potential or a known electric field. Okay, so we're also sometimes interested in our energy density. There's our dipole flux lines from the last video. So sometimes we're interested in our electrostatic energy density. And so how can we find that electrostatic energy density? Well, we can just get this from our general equation for the total energy in the volume. And we can say that our lowercase w sub e is our energy density. And this is just going to be the derivative of that total energy with respect to our volume. And that is just going to be the integrand of our previous boxed equation. So we now have 1/2 times d dot E, and so from the same arguments as before, we can say this is 1/2 epsilon naught magnitude of E squared, or sometimes you'll see it written as d squared divided by 2 epsilon naught. And so that's how we can find our electrostatic energy density. So in the next video, we're going to take a look at a brief example to conclude this unit on electrostatics.